All right, good morning, everyone, and welcome back to another session in our Civil Engineering for the Future webinar series. And I think this will be our last webinar session 2025 until we meet again in spring 2026. So we are so fortunate. So we have Dr. Anushka Mishrra from Duke University, Durham, North Carolina, with us today. And thank you, Dr. Mishrra, for accepting our invitation and agreeing to share your expertise and enlighten our audience with your research work. So let me first start with a quick overview of her incredible research journey. So she's currently working as a postdoctoral associate at Duke University. She's working with Professor Helene Shu Kim, and she works on critical mineral extraction from acid mine drainage and related treatment residues. She's also currently a fellow of the Critical Mineral Hub at Duke. She completed her BTech in Chemical Engineering at National Institute of Technology, Tiruchirappalli, and she continued her master's and PhD in Energy, Environmental and Chemical Engineering and Washington University at St. Louis. So she was close to SIU, okay? And then before joining Duke, she completed another postdoc at UC Berkeley with the renowned Professor David Sedlak and Professor Bashio Mi, where she developed sustainable treatment methods for removing hexavalent chromium from groundwater. She is also a recipient of American Waterworks Association Abel Wollman Fellowship for her work on lead release in drinking water pipes during her PhD. So we are truly fortunate to have her with us today. So without taking much time, I will let Dr. Mishrra share her research. And so the presentation will be roughly like 45 minutes, and then we can allocate the last 10, 15 minutes for the question and answers. So for the audience, if you have any questions that you like to ask from Dr. Mishrra, so please feel free to drop them in the chat box. All right, Dr. Mishrra, over to you.
Thank you. Thank you, Himali. This is such a kind introduction. I'm very happy and I feel very honored to be invited for this webinar series and present my research. So, like Dr. Himali here mentioned that I've done a couple of different type of research over my academic journey. So today I just plan to share my research that I did at UC Berkeley and I'm currently doing at Duke University. And this is basically looking at how we can advance water treatment and critical mineral recovery. And the whole idea about moving the energy, environment, and health nexus forward. So so happy to be here. I just want to um, like I just share what expertise I've gained over my whole trajectory. So when I started my graduate research at WashU, I primarily focused on environmental water chemistry and water quality monitoring. So lead is a legacy contaminant in the Midwestern United States, and while it is banned, we still have problems with lead pipes. So this lead can be released into our drinking water supply. So I looked at that. I also looked at how alternative water supply is growing in the West and also affect lead release. So this was my PhD, and I picked up a lot of skills on water chemistry, aquatic chemistry, kinetics, and other database approach to tackle this problem. From there, I went towards the West actually and worked with Professor David Sedlak and Paukshia Mi on creating this water treatment technology for tackling chromium 6 in the groundwater supply. And back like a year back, and even like few years back, they were trying to regulate chromium 6 in California. So this is still an important research topic in the region. And if the chromium is regulated in other states, then we definitely need more new water treatment systems that can sustainably remove chromium 6. So part of my talk today will be on this. I will go deep on it. And right now, I've just been a couple of months, I've joined Professor Shikim's group, and I'm here studying about how we can recover critical minerals from acid mine drainage waste, which can be both acid mine drain discharge and treatment solids that are present in the different coal mine sites. So applying my environmental geochemistry skills and hoping to see get a better understanding of how these solids can be used as a source for critical minerals. Um, like I said, today my focus is on the water treatment and resource recovery, and we will focus on how sustainable materials and approaches can be developed to advance both the directions. I will start with my first project that I did as a postdoc, which is creating this filtration media to remove hexavalent chromium from groundwater supply and meet the stringent chromium uh, regulations set to have a clean, safe water. So just want to briefly touch upon why this is important. We all know that chromium can both act as a micronutrient if present in the oxidation states of 0 and 3. But at the same time, if you have a chromium 6 oxidation state, it can be very soluble in water. And at drinking water conditions, we can see easily any concentrations of chromium 6 because it's all soluble. For the toxicity, a lot of research has been done on this, and there are primarily a few ways you can be exposed to this. One is through inhalation, and the other is through oral exposure. So the inhalation exposure definitely leads to respiratory cancer when you exposed to a lot of chromium 6. For the oral exposure, most work has been done on mice models, and so it is shown that it can have gastrointestinal cancer issues when you're exposed to chromium. So in the United States, chromium 6 is being regulated, but also whole of chromium is being regulated. So US EPA, Environmental Protection Agency, has 100 micrograms per liter maximum contaminant level for the chromium in all the oxidation states together, whereas California State Water Board controls both chromium 6 and total chromium. And this is because they have a lot of natural sources of chromium 6, because chromium can be introduced through anthropogenic activities most of the time. California, on the hand, has actually soil minerals that are rich in chromium 6. So, and sorry, in chromium, then through oxidation, it can be released into the groundwater supply. So they control both of it. And in 2025, actually, they lowered this chromium 6 level to 10 micrograms per liter. So it's important that when we go from 50 to 10 micrograms per liter, we have treatment systems that can still get to those low concentrations while not adding the cost to water treatment. So the map here on the right is basically looking at the chromium levels in the well water across uh, the whole state of California, and this data is compiled over a decade. What you see here is like the warm colors means high chromium concentration. So some of them are like, there's a lot of points in the Southern California and some in the Central Valley. And then the lighter color means that they're low concentrations. The question here is, now that we have lowered the chromium 6, even the colder colors like the purple and the blues also become an important source of contamination for drinking water supply. So what do we do? Um, there is a lot of work done on nanomaterials, and one of them is molybdenum disulfide, and it interacts very well with metals. It undergoes redox processes. It can also undergo adsorption. So molybdenum disulfide has been studied for removing chromium 6 from the water. What we want to do is being able to take this nanomaterial to a scalable treatment technology. So, like I said, there is established work on how chromium 6 can be reduced to chromium 3. So that is the attractive property of MOS2. Molybdenum disulfide can actually undergo redox process with the chromium 6. Then the chromium 3 becomes non-toxic when you handle the final product after the reaction. And there are different phases of molybdenum disulfide that interact differently. For example, here, the red curve is the 1T dominant phase of MOS2 that actually undergoes the redox process. And there is another phase called 2H, which actually undergoes adsorption. So it's just going to remove chromium 6 through adsorption, but not transform it to chromium 3. So we're interested in looking at one of these phases and how we can transform, like remove the toxicity associated with chromium 6 during treatment. However, like I said, nanomaterials pose a lot of challenges. There is the use of nanomaterial itself can be potentially hazardous if there is nanoparticle release, and we can also have problems with the aggregation of nanomaterial. They seem to, over time, become larger particles and lose their efficiency. And then there is also issues with water permeability. So if you're looking at a scale up technology where you want to run the water at high flow rate, having a nanomaterial can often block these sites where the water can flow through. And so that is one of the problems that is associated with using a nanomaterial itself. So part of my work was to understand and find a substrate that can really host the molybdenum disulfide very well and create something that is very porous in nature, and yet we have the nanomaterial constantly interact with the metals in the water and the oxyanions in the water. So I tried a couple of different porous medias. Here I've highlighted some of them. Um, Granular activated carbon can be a very attractive substrate if you think about it, but it itself undergoes a lot of reactions with the molybdenum disulfide, so it didn't really work well. But if you have something like a wool, it can be a mineral wool, cotton wool, we start seeing some interactions between the nanoparticles and this material. And the best that worked for me was cotton wool. The cotton wool's properties, like it can absorb a lot of water, actually helps, because when we put the cotton wool in a MOS2 water suspension, the MOS2 immediately absorbs onto the wool, and if you dry it, it can really bind well with it. I think it's something to do with the cellulose structure and how the sulfur atoms in the MOS2 bind with them. And definitely there's scope for more research on how that interaction happens. But during the synthesis process, we were able to coat a good amount of MOS2 onto the cotton, which we think would be able to, react with chromium-6 during the treatment. So part of this work involved characterizing this material. So we are looking at the nanoparticle size after we have coated it on the cotton. We see that there are 220 to 255 nanometer particles. We also see some aggregates, but the number of these aggregates seemed lower, did not seem to be a bigger fraction of the material that we coated. We also wanted to make sure that during the synthesis process, we did not lose the phase that we want. So we can control the type of phase we want for the MOS2. And we just create that phase first and then run the synthesis of the MOS2 cotton. So we did not lose much of it. We have still retained the MOS2's 1T dominant phase on the structure. We did this analysis using XPS. Then we put the material under the microscope. So what here you're looking at are cotton threads, which are at least 10 micrometer in diameter. And the bright particles, like the bright regions on it, is definitely the particles. And so the way to know that these particles are MOS2, we did EDS, which is looking at the elemental maps on the carbon fibers. And what we see is that most of the surface is coated with molybdenum and sulfur. And like I said, there is more scope of research to examine how we can have a complete coverage and yet not lose a lot of MOS2 due to overloading. Like we can prevent that. So through these characterization techniques, we were able to come up with a media that, like the big percent of MOS2 that we need, that really worked for us, and how we can prevent a lot of MOS2 loss just by flushing the cotton surface. So once we prepared this, we did some studies using batch experiments. So like you can see the small vial over here, we have the cotton suspended in it. It's just like any other wool. And we had a lot of chromium that we loaded onto it so that we can see the effects in a larger scale. So we ran with 10 milligrams of 10 milligrams per liter of chromium-6. So I'll walk you through each of the different characterization we did. So first we wanted to see the absorption capacity of this material, and so we ran it at different concentrations of chromium to see how much it can remove. The first effect that we saw is that pH had a big impact on how the chromium-6 is removed. So lower pH means higher chromium-6 could be removed by the media, and higher the pH, there was a drop in the removal efficiency, which means if we apply this material for drinking water purposes, which is usually neutral pH, we can see that lesser amount of chromium maybe the material won't run at its maximum capacity. We also saw that the kinetics at different pHs is different. So the neutral pH conditions actually have slower kinetics of chromium removal versus the lower pH kinetics. And when you run the chromium, when we were able to load more chromium into the water, we could start seeing the different oxidation states. So the red bar over here on the right, the bar chart. So the red region shows all the chromium that is on the material, and the green or the part of it is chromium 3 that is in the water after the reaction has taken place, and some of the remaining chromium 6 in the water after the reaction has taken place can be seen. So with confidence, we can say that the material can remove 75% of the chromium from the water. Of this, 10% is, of the remaining 10% is at chromium 6 and 10% is at chromium 3. So overall, it's seemed promising at higher concentrations of chromium. We also did some XPS characterization for the material to see what phase of the chromium existed on the cotton itself after the reaction took place. And we saw that for all the pH levels, chromium 3 was our dominant phase. So it could be confirmed that the chromium 6 was in fact turning to chromium 3 on the surface of the MOS2 cotton. So with that, we actually went ahead and looked at the reactions carefully. So we know that there is redox happening where the chromium 6 is going to chromium 3 through MOS2. And you can see that in this process, it's consuming the protons and creating hydroxyl ions. We also have another method of sequestration, which is once you have chromium 3, which is actually positively charged, whereas chromium 6 exists as an oxyanion, so it's negatively charged. So once we form this chromium 3, the chromium 3 can interact with MOS2 because MOS2 actually has a negative surface charge around it. So we think adsorption can also take place for sequestering some of the chromium 3 on the surface that we saw through XPS. And then finally, we think if we give enough time for the reaction to go forward, this molybdate that is released during the redox process can actually interact with chromium 3 to form precipitates like chromium molybdate. However, I think that needs more time for reaction. And usually when you have water treatment systems and like filtration units, they actually have lesser contact time. So this is something we can also study in future and see if these pathways can help us remove more and more chromium from the water. So for the treatment purposes going forward, I will show you some data that we ran at scale. So we're looking at chromium 3, but at the same time, we want to be sure that the MOS2 is not a secondary source of contaminant, saying that it releases molybdenum in the water and that becomes toxic. So we will be looking at both of them to see how this technology works for removing chromium 6 from groundwater. So to do these, we did a lot of column-based experiments to mimic our real-time filtration systems that are out there. They usually there for activated carbons, but you also have ion exchange columns. And so all these columns, they have like a contact time, and typical contact time ranges from 5 to 10 minutes. So we went with 10 minutes. We had this 5-8% of MOS2 on the cotton. And so we kind of stacked them in the column. A little bit amount was lot actually to a lot of water can be reacted with a little bit amount. So we had some of it kind of in that column. And we ran just water through these columns continuously. And so each bed volume here basically represents 1 milliliter of water that has flown through the column. And so for a very small amount of filter that we loaded, we saw that about in 1,000 bed volumes, or let's say 1 liter for every 12 milligrams of MOS2, we saw that the treatment reached breakthrough. What is interesting that these bed volumes can be translated to bigger scale units. So if you have the same ratio of your material versus the water that is reacting, we can still use this bed volume calculation directly. So for both authentic groundwater that we procured from one of the water districts in California and synthetic groundwater that we made in the lab, we see similar performance, which means that the differences may be just coming from the lack of organic matter in our synthetic groundwater, because that is sometimes hard to mimic. But we didn't see a big difference. So we just proceeded with all our experiments in synthetic groundwater. So like I said, we're looking at this chromium 6 and it's slowly getting removed from the water. And slowly the material is exhausting. So by 800 bed volumes, the material is completely exhausted. And at the same time, I also tracked molybdenum concentrations in the water. Now, what is important to remember is that molybdenum does not have an MCL right now. It just has an advisory limit set up by the Environmental Protection Agency. And there's also a WHO limit on molybdenum. So it may become important in going in the future. So anyway, we tracked this molybdenum that was being released, and what we saw is that while the material is removing chromium-6, it is releasing molybdenum in the water. So that is concerning because we don't want people to drink molybdenum in place of chromium and then have different health effects. So we could see that this is happening at groundwater pH conditions. If we revisited the whole mechanism over here, what we saw is that the amount of molybdenum released, which is 150 micrograms per liter, is actually much higher than the amount of chromium-6 being removed from the water. So the ratio is such that for every mole of chromium removed, there is 0.3 moles of molybdenum that should be produced. But we saw that more amount of molybdenum was being released. So we wanted to understand why this is happening. And our hypothesis was that the oxygen in the water was reacting with MOS2 to create more molybdate species. There is also some preliminary work done on this where they've shown that MOS2 can be oxidized in the water. So we wanted to also study this and see if our hypothesis was correct. So to do that, we basically ran our columns in anaerobic chamber. So we could control the dissolved oxygen in the water. Basically, we ran water that was completely deaerated, and then we looked at the chromium. So now what you're looking at is my previous data, which is in the orange circles and stops at 1,000 bed volumes. And we are also looking at an oxygen-free system. Basically, there is non-detectable amounts of dissolved oxygen in the water, and this completely increases, like significantly increases the treatment capacity for the material. So it has gone 17 times higher than we would have seen in a normal system where we probably predict dissolved oxygen to be present in the groundwater. At the same time, when we look at the stability, we saw that this lack of oxygen actually helped us decrease the amount of molybdenum in the water that was coming out of our columns. So the water coming out of the treatment system now had very low concentrations of molybdenum throughout the process, which kind of confirmed our hypothesis that oxygen does interact with the material and is one of the ways the material is destabilized, even like mostly due to oxidation. So this results kind of help us think about how we can strategically design a treatment system using MOS2 and cotton to treat water, such that at some stage we can remove the oxygen prior to treatment. And also in many states, many areas in California, because it's a groundwater, actually the groundwater can have low dissolved oxygen concentrations. So this kind of also helps us understand that if a small scale water treatment were to be installed, they could see a varied result just based on the dissolved oxygen levels in their water. So this is kind of an important finding. Part of the intention of this work is that we can show that it can be used as a viable treatment technology, and we wanted to see that after we ended up running the treatment, we still had a lot of material left, how we can reuse it. So one of the ways to reuse the material is to simply clean the material. And so we tried a lot of different types of ways to do it. The most effective method was washing the filter with hydrochloric acid. And actually, it proved very helpful because it did not really um, dissolve the MOS2. It's very stable under acidic conditions. And we also noticed that through this process, all the chromium that got out of the material during cleaning was all chromium free. So we're looking at non-toxic hazardous waste coming out of the cleaning process, which kind of lowers the cost of water treatment. And for the oxygen-free system, where we see the material has very high capacity, we see the chromium-3 that we recovered from the material going 10 folds up. And also, if you see the molybdenum has gone like 100 folds down during the cleaning. That means that if you ran the system in deaerated conditions and cleaned it, the material is extremely stable under those conditions. And so definitely more viable option to run this under oxygen-free conditions. So to test the reusability of the filter media, we cleaned the filter after it exhausted and then ran it again a couple of times with the water. So in a, like I said, in a normal air flow system, we see that the material only shows like about maybe close to 3,000 bed volumes of performance before it breaks through. And I want to mention that the reason I show the breakthrough at 100 micrograms per liter is because the EPA has set a limit of 100 micrograms per liter, so we can at least wait for the material to reach that concentration. Um, see when that happens. But for the oxygen-free condition, when we clean the system, like clean the filter and run it again, it can still go for another 10,000 bed volumes, which is again promising because it expands the lifetime from 27 to 30,000 now. 17,000 to about 27,000 bed volumes of treatment. So why is this important? This is important because currently in California, there is ion exchange columns that are being used to remove chromium-6. And it's a very good technology because it can really treat very high volume of water, like 35,000 bed volumes, and if run in correct conditions, even higher. So our aim is to create something that can match these bed volumes and not simply be a technology for the sake of it. So we could show that under oxygen controlled environment, we can get to somewhere closer to ion exchange system. However, more work needs to be done to get there. However, there are some advantages that this material has over an ion exchange system. First is that the groundwater that we treat using this filter um, has no more chromium 6 in the system, and we have all chromium converted to chromium 3, which is non-toxic, whereas the ion exchange simply removes the chromium 6. And when you clean the ion exchange resins, they still have chromium 6, so it's a hazardous material, and it increases the cost of the like the water treatment and the cleaning associated to a lot. So that's why a lot of smaller scale water treatments hesitate using ion exchange just based on the cost involved in procuring these resins, cleaning these resins, and reusing them for long term. And the second advantage that MOS2 cotton has over ion exchange is that the MOS2 cotton, like we show, can work with groundwater pH conditions, which is higher than ion exchange. Ion exchange works at low pH conditions, pH 5.5 and like 6, or maybe a little lower than that. It only performs well at that conditions. At higher groundwater pH conditions, it does not work well. So if we had to compare like apples to apples, we could potentially check how MOS2 cotton works at lower pH. But ideally, if we can get away with having to add chemicals in the groundwater to lower pH, it's good that we can just treat the groundwater as it is and not have to change the pH. So that is, I think, a plus or an advantage to the whole way MOS2 cotton works. So this work we recently published in ESNT. You can read more about how we did more hypothesis testing with what kind of chromium is present on the media and what kind of reagents can be used and what are the long-term impacts of using such a treatment system. Um, I'll take questions for this at the end of the talk, but I'll move on to my second research, which is I'm doing at Duke right now. This is more focused on using environmental geochemistry to understand these different solids that are present and how they host critical metals, including rare earth elements and other transition metals that are important for clean energy technologies. This work I am doing is with Professor Helen Shi Kim. She has done a lot of research in this area prior to my work here. And so I'm happy to share some of that today. Basically, over time, this work has been done where people have looked at coal-based waste, including fly ash and even mine drainage, and looked at how rare earth elements can be extracted from these systems. So essentially, the research so far has been reporting concentrations of RE found in these coal-based waste, which makes them an attractive resource as a secondary source instead of having like a proper mine or an ore for the REs. So it creates a market for the use of these coal-based waste to get critical metals. However, there are a lot of challenges in being able to extract the rare earth elements from coal mine drainage, just because of the vastness of coal mine sites in the US. So you have a lot of regions in the US that have coal mine sites that are abandoned or that are still present, but the variety that exists in the different chemical composition just based on the site or the region of where they exist kind of affects how we can create a more mainstream extraction process, because we need to I think the extraction process need to be tailored on how the acid mine drain waste look like. And then, of course, based on the pH conditions of these mine waste, different strategies need to be created. So if you have an acid mine drainage, you're looking at low pH conditions, but there are many other mine drainage sites that are actually high in pH conditions. So accordingly, you have to create a extraction process based on that. And then some of the waste are solids, so you have to create a different extraction process. So there's a lot of variables in this strategic removal of rare earth elements associated with coal mine waste, which kind of brings us to our project where we want to focus on acid mine drainage. This is because a lot of literature right now shows that at lower pH conditions, we start to see high rare earth element concentrations in the drainage, we can call it fluids, so in the acid mine drainage fluids. And that makes this acid mine drainage fluid an attractive source. And like you can see in this region, the Appalachian region, there are like a lot of acid mine drainage streams, and all of those data points have been put together to see what the concentrations of RE extracted can look like. And they can be somewhere between 800 to 3,000 tons of RE per year, or at least 700 to like 2,000 milligrams per kg of REs, like in terms of just like the solid. So that kind of makes it like a very good, I want to say secondary source, but very close to even the primary sources of REs existing in the US. So we are interested in understanding how they're associated with these different acid mine drainage sites, and what factors we should consider when we are trying to do the extraction. Before I get into that, I just want to highlight that when I say REs here, I'm talking about all the REs that are present in the lanthanide series, and also yttrium and scandium together. So all of these combined, the concentrations reach as high as like 1,000 milligrams, micrograms per liter. So because, like I said, there is plenty literature that tells us that acid mine drainage sites are a viable source for REs. There has been different type of treatment systems designed. Part of the reason these treatment systems were designed was to reclaim acid mine drainage waste, because they are acidic in nature. They can impact the environment around them and can also disturb the water supplies and other systems, ecosystems existing. So part of the reason treatment systems exist are basically both to reclaim the coal mine sites, but also use that opportunity to extract valuable metals out of it. Some of the ones that I'm showing here was published by Ben Hedden in 2019. So these are some passive treatment systems. Basically, they have like limestone beds, different settling ponds, and so as the acid mine drainage stream is diverted into these uh, kind of systems, they can help, first of all, make maybe acidic mine water to more basic in condition, so it's less harmful. And then also in the process, extract some of the metals that we care about. And some of these are setting ponds, low pH iron removal. There's also vertical flow pond, which means that the mine drainage is actually going into a more porous structure, and it has a lot of stratified layers, so it reacts vertically down and then exits from the limestone bed. And of course, like I said, there are definitely different type of designs around how limestone beds can be used to treat them. There's also active treatment systems that I've not shown here, but basically they use sodium hydroxide directly to immediately neutralize the pH and remove solids that are precipitated in the process. We look at some passive treatment systems, and our group over here actually, even before I joined, has actually done some sample like sites. They visited the sites and done sampling. What they've done is for each site they have visited, they've collected treatment solids, and they have taken influent like the drainage stream. Um, they collected those fluids, and for each site we've looked at now the RE total RE concentrations. So in this graph on the right, you can see that in the acid mine drainage fluids, you have low concentrations of total RE, like around 200 micrograms per liter or 400 micrograms per liter. But you can also have very high concentrations of RE, which makes those kind of um, acid mine drainage waste actually valuable. So up to 1600 micrograms per liter, which is very high. And when you look at the same sites and the treatment solids, now you see more REs in the solids, and which is very interesting because a site that we would probably not look at because it has low REs could be valuable in terms of the treatment solids that are there, because they may have now enriched amount of REs in them. So this is very interesting. And I think what's even more interesting is that every site has its own concentration, that there's variability involved. And I think it's coming from the fact that all of these different systems have different type of chemical composition. So here's Ben Hedin on the right in that picture there. He was helping us do some sample uh, removal from vertical flow pond. But like I'm showing some systems over here. They have limestone beds, which probably is giving this color, and then also helping neutralize the acid mine water. We also have one here, which is active treatment system, RASIC. So they have these sites are turned over multiple years. So there's opportunities to excavate the solids and work with them. Like I said, so these um, acid mine drainage fluids have like different chemical compositions. First is that they have very high amount of iron, aluminum, calcium, magnesium, and other alkaline metals, and also very high amounts of sulfate, because basically they are like iron sulfide minerals turning into acidic waters. So these metals exist in a very high concentration. We're looking at the orders of milligrams per liter, like tens and even close to hundreds of milligrams per liter. And at the same time, when you compare the critical metals, they're present in micrograms per liter. So we're looking at maybe 500 or 1,000 or even like 50 micrograms per liter of these REs. So this big difference in the different type of metals present in this acid mine drainage fluids actually make it difficult for extraction. And also partly the reason why rare earth elements are called rare, not because they're actually less, but the extraction process is really tough around rare earth elements, because we have other co-associated metals which are present at high concentration. So going back to the same data that I showed you previously, the other important aspect of this plot is that I have grouped these data points based on how the fluid and the solids are enriched. So you can see that all the blue triangles are basically solids and fluids that have high concentrations of aluminum, whereas the orange points actually have high concentrations of iron in it. And there's one point that we have that is uh, rich in manganese in the fluid. So this came from this idea that now that we have such high concentrations of different elements, can we actually group them into like categories of enriched solids? And so of the 7-8 sites that we have studied, we've tried to group them based on the influent, like the fluids. And you can see that there are more sites over here in our groups that are aluminum rich. Basically, more concentrations of aluminum is present in them. And then there are some sites that have more concentrations of iron present in them. And there's one site that we definitely could get samples from that had more amount of manganese present in them. So the differences in the iron, aluminum, and manganese concentration will drive how much amount of REs we see how we extract these REs going forward, what kind of treatment solids are formed. So it answers a lot of questions. And so we are also investigating this. The other way to look at this is just to dig into more literature and see what they have reported, and if we see a clear pattern in how these enrichment actually helps answer some of these questions. The other thing, like I said, how this enrichment happens is we can look at a partition ratio. This is basically all the REs going from solids to influent. So you can see for the manganese enriched fluids, we have the highest partitioning ratio. This is because in the AMD fluid, there were low concentrations of RE, versus in the solid, we had very high amounts of REs comparatively. So that's why the partition ratio is high for it. Versus for the irons, we see like consistently low partition ratio. So if we were to design a extraction process using an iron enriched AMD fluid, the maybe amount of REs we can extract may be just lower based on this estimations. The aluminum seems to be at a broader range where we can see high partitioning happening for like active treatment systems, whereas low partitioning happening for maybe some passive treatment systems. So this is for individual REs and yttrium, but yeah, we can start seeing some trends develop for different types of rare earth elements present in the system. So my major area of focus is to understand the solids, characterize them, and understand what associations exist between the REs and the host minerals. So I have done a lot of surface characterization, basically putting all of these residues that we have right now, solid residues that we collected from the sites under like microscope, and just to look at first question is what are the host minerals. We know from our ICP-MS data, like elemental mass based measurements, that we do have manganese, aluminum, iron, but what do these solids actually look like? So here's the picture I took for some of the particles collected from the site Sterret. um, the key difference is that influent water was very rich in manganese, but the residues actually started having more aluminum present in it. So that's interesting that we have now abundance of aluminum in them. At the same time, we also have manganese in it. So when we look under the microscope, SEM, and do an energy dispersive X-ray spectroscopy scans, so EDS scans, which is basically creating elemental maps, we start seeing that aluminum, manganese are like coexisting in these solids. There's possibility that manganese is like covering aluminum solids. And we see also that iron is actually very less in concentration. So I've run this EDS scans on several solids like that we have collected, and this is just one of a representative image that I'm showing over here. So there was like this, we can generalize from here for just this site that more aluminum and manganese present in the treatment solids versus iron. And the other thing we could notice is that most of them were all oxides. So the treatment solids that are being formed at any abandoned coal mine site or any coal mine drainage site over long term of period are forming these oxides of aluminum, manganese, and iron in them. Now, we sampled so many sites, so it's worth comparing some of them. So here I will draw a comparison between Sterret and US91. What is interesting between the two is that when you look at the residues, both are aluminum rich, but the influent was different in the enrichment. Sterret had more manganese enrichment, whereas US91 had more aluminum enrichment. So the fact that the residuals ultimately have aluminum, it's like worth comparing to see what's the differences. One of the key differences is that there is, even though more manganese present in the fluid for US91, we didn't see any manganese in the treatment solids. And in fact, we saw mostly aluminum and silicate present in the treatment solids, like you see here. There were also some diatoms that I could see under the microscope. So it's interesting, like how we now don't have enrichment of manganese in it, but we have more enrichment of aluminum, silica, iron, and definitely oxygen all over the treatment solids. There is one other that I would like to also compare with US91 is Jennings. The reason I bring this up is for the same reasons, that the residues is very rich in aluminum, but the influent is now rich in iron. So if you had like a very enriched iron fluid, do you see iron precipitating out in the treatment solids? The answer is partly. I don't think all of the iron ends up precipitating in the solids. We see very less iron around these particles. And the fact that there's a lot of aluminum present with silicates makes me think that when you have these residuals showing dominance in aluminum, you're definitely going to see a lot of aluminum. But the secondary element that is dominant may or may not show up in the maps. For example, just going back real quick, stearate manganese we were able to see, but here iron we're just barely able to see across these scans that we're doing. Also to remember that these are for surface characterizations, SEM, like the limit of these scans is maybe more superficial, like in the um around solid and not bulk characterization techniques. So the next step is to take these same solids under microscopes that can do more fine scale characterizations like micro XRF or XAFs. They can help us actually look at bulk characterization and see where the REs are sitting and if it's inside the solids, outside the solids. The other limitation of using an SCM is that if you have very less amount of REs, for example, in this case, the weight percent of REs is like less than 1 weight percent, it cannot be captured easily using an SCM technology. But it is definitely a helpful technology to look at more abundantly present elements like I said, iron, aluminum, and even silica that has shown up on our maps. So it's a definitely good screening uh, process. And I think the next steps in my research will be looking at more bulk phase characterization and being able to detect the REs and being able to see them on these scans. With that, I want to just um, summarize the research efforts and the directions that we are going from here. So what do we want to answer? We want to answer the major elemental composition of the feedstock, and we're getting some good ideas about how this is, not only from our own sampling, but also from the literature that exists. And now we're starting to identify the host mineral composition, and we still may not know like the actual form of oxides or silicates that are present. More work needs to be done, but we can start identifying there's an aluminum, there's a manganese dominant phase, there's an iron dominant phase, silica dominant phase. So we are getting there. Of course, the next step is to see where the REs are, where is the cobalt, where is the transition metals, where do they sit on these different phases. Based on this understanding, we will go ahead to design strategic separation technologies where we can maybe treat the water or treat the solids to um, separate just the REs or the cobalt, which is also critical metal, out of it. So develop some strategies based on our understanding of these. And then finally, use this geospatial data that currently is available. USGS is starting MRI, I think also does the same thing, scan solids across these different sites and uh, establish a geochemical database that can potentially be used to create more understanding of how critical metals can be resourced, what sites should be targeted, and what processes can be used to um, extract them. And so with that, I just like to wrap up and acknowledge all folks who have been very critical to move this research at Berkeley. Definitely want to thank my professors, but all the graduate students and the undergraduate students who have helped me during the process. And at Duke also, I'm grateful to our former graduate student, Anna Altman, and external collaborator, Benjamin C. Hedden, who has helped us procure these samples from different sites, and definitely the funding agencies who are critical in making the research go forward. I'm very happy to take questions. And yeah, I'll open the floor to all the audience.
Thank you, Dr. Mishra, for the excellent presentation, and it was really interesting. So you talked two major research areas, and both of them were really interesting. So now the platform is open for any questions from the audience. So if you have any questions, feel free to unmute or ask yourself, or else you can put the question on the chat. So until the questions pop up, let me ask few questions.
Yeah.
So I had questions from both sections, but let me start first with the rare earth element section. So I know, since I'm also working in this acid mine drainage, so I had this concern when analyzing the metals, because there are high metal loading in
Yes.
iron, aluminium, manganese. So when we try to analyze each of the metal, so the other metal can be an interference. Okay, so it can be a huge problem when it comes to rare earth elements, because the concentration is significantly low compared to these major metals.
Exactly.
So what kind of analytical methods will you be focusing when it comes to the rare earth element analysis? So
Yeah, this is a very good question, because this is like this is why we are doing this, because there is a big difference in the concentration, like you mentioned. There are high metal loadings for iron, aluminum, manganese, and low REs. Or one of the techniques, like, is the way I have been able to show you data over here is through doing ICP-MS, which is
mm,
basically mass spectrometry. So we're getting numbers out of these, and um, we are also looking at like what interferences maybe iron or aluminum manganese has. Luckily for the rare earth elements, um, the interferences, like for the iron, would actually be at a higher, like the atomic weight ratio interferences that we have actually don't really reflect much on the REEs. So we are able to use ICP-MS to measure them. However, for SEM, let's say REs are low, but cobalt is a little higher than the RE concentration. And so when we do those analysis, the iron that we are detecting can easily interfere with cobalt. So
mm,
you cannot detect like how much cobalt is present just because you see a large peak coming from iron. And these
mm,
kind of challenges will also exist when you start looking at different characterization techniques, like peak overlapping. And I think for the MS, it's right now very like clean. We don't see much of interference because um, I think the ICP-MS, not OES, ICP-MS can do low concentrations of REs very well. But I think the challenges will be when you start doing more uh, imaging. Imaging will be definitely a challenge. So how do we tackle that when we do imaging? So I think that we try to remove these host
mm.
like metals before we can image them would be a good way to do it. We have to figure out how. Um, there's some papers I've seen on like precipitating solids out of the water
Mhm.
to see where the REs can be enriched, and then putting them in the microscope could be one technique. Uh, but I think that is why we are looking at other type of imaging techniques like micro XRF or um, XAFs. They can look at more amorphous solids, and maybe we can get some images out of that. But this is a challenge. I I am trying to think of more ways, but if there are some selective separations that can be done, that would be very helpful. Especially if you just look beyond rare earth elements, cobalt, manganese can also be a good critical metals, and there's definitely interferences in, like, you cannot separate the manganese from cobalt, you cannot separate the iron from some metals. So those kind of challenges, yeah, they will be there, and hopefully we will have some answers to doing so.
Yeah, then once you found that answer, then we can invite you again to see how you
Yeah.
tackle that one. Yeah.
No, I mean
So,
also, like, if you see the passive treatment systems that people have
mhm,
built right now, they have these limestone beds, right? So the idea is to increase the pH of the water, so we precipitate like different things out, and then maybe hopefully in those precipitates we see some enrichment of REs happening enough that we can then do some imaging and uh, measurements based on it.
okay, yeah, yeah,
Yeah, yeah.
yeah. So in your presentation, so you talk about residuals. So are these residuals like the limestone you
Yeah.
extract solids extract from the limestone beds, right?
Yeah. So I've
Oh,
shown
okay.
you like those settling ponds and the
Mm-hmm.
limestone beds. So if you look at them, they basically look like soils. So all of these treatment solids have formed because the acid mine drainage reacts with the limestone bed, and then they've suddenly precipitated out tons of iron and manganese and all of these silicates. And so we've just taken them and we call them residuals of the treatment system.
Yeah, I think there is a question
Yeah.
from the audience, but I
Yes.
am not sure how to unmute him.
Maybe you can unmute all or like
Hello, Mike. Okay, I think now he should be able to speak.
Oh, yeah. Am I
Yeah,
yeah.
audible?
yeah.
Okay. Thank you, Anushka, for your nice presentation. So I am joining from the Japan. So it's already 19 and 1 a.m. in Japan. So I'm doing PhD currently in the Kanazawa University.
Okay.
And my research topic is very closely to your first research.
Mm-hmm.
So currently I'm doing to like synthesis functionally cellulose material,
Mm-hmm.
and application is for the most toxic element like arsenic 3,
Yes.
selenium 4 and 6, and the chromium 3 and 6 4. So for your first research I have some question, and it's like, so you like add the molybdenum sulfate synthesis with the cotton, like some
Yes.
cellulose material. So my question is, do you know the like we use the degree of substitutions, one term, like how much the functional group attached with the cellulose? Because like cellulose is a very big molecules and there is a lot of OH group. You can
Yes.
substitute the your functional group. So do you have
Yes.
any like data or you check like how much it successfully you functionalize the cotton with this
Yeah.
molybdenum sulfate? Because you showed that like the ion exchange resin currently have a much more bed volume compared
Mhm.
to the your product. So if you increase the like the degree of substitution, that case
Yeah.
of course the capacity of the material will be increases,
Yes.
and then it will be almost equivalent to the I think the bed volume of the ion exchange resin. And I
Yeah.
already read your paper from the your EST when it
Thank
was published, and I follow you and your professor from the LinkedIn actually for
thank
long.
you.
Yeah.
Yeah. So it's a very good question. Um, I totally agree with you that there is an opportunity. If we increase the amount of MOS2, we can increase the capacity of the material. And when we were creating this material, if you, I put this in the paper. So we've checked lower loading rates for sure. We were checking 1, 2 weight percent, 3 weight percent, 4 weight percent, and even we have also checked. So I have shown you data for 5 8% of MOS2, which is like for every 100 milligrams, you have 5 milligrams of MOS2 loaded on it. We've also looked at 10 weight percent of MOS2. The reason we abandoned the higher weight percent is that when I have, instead of 5 milligrams, I have 10 milligrams. If I've not done the coating process very carefully, my MOS2 will be hanging loosely from the cotton. So when I am just running water from it, all of the MOS2 just gets released as particle, like,
Mm,
flushing away from the surface. So I don't, right now, I don't know why this is. So like when you have higher weight percent, the MOS2 just doesn't stick to the cotton, but just, creates more sandwich layers on top of other MOS2. But I think like working a little bit more on the synthesis process, maybe we can increase the capacity of the moisture. It's a good question. It's definitely something that I probably want to study in the future. Like, what is this loading that we can get um, to of MS2 where we can have all of it and then not lose any of it, right? So we've done the range that I have checked is 1 to 10 8%. And what I've found is that 5 8% was like a good in between number to work with. 10 8%, maybe it's just how I was working with it, like the coating. It didn't work successfully for me. Like I saw a lot of MOS2 that was just falling off. So um, if there's a way that you can render the cotton to stick more MOS2 on it, that will actually help increasing the loading weight percent. The other thing that we don't know yet is how the cellulose is binding with MOS2. So cellulose is a negative, like the surface is negatively also charged in the water, and then MOS2 is also negatively charged, and yet they can bind very well. So if we can work more on that, how that interaction is happening, maybe we can crack the code to how more MOS2 can be loaded onto these cottons. So definitely, yeah, worth exploring in
Yeah,
future.
I understand, and I have some idea. Just I want to share with you. Like, yeah, it's happened. Like when you bind some group to the cellulose, sometime like it's increasing the groups and binding loosely, and just only water leaching experiment you can lose this molybdenum. Or sometimes like I try to like if you want the nanovalent iron, we try to grafting to the cellulose. Like if you
Yeah,
increase the concentration, then the water leaching, the manganese or the iron is come out to the water.
yeah,
So that
exactly.
cases you maybe try some the linker. So some linker group that are insoluble in water like epoxy or the
Hmm.
simple silicon dioxide molecule, titanium dioxide molecule. If
Hmm.
you use a linker with the your functional group to the cellulose in the middle, then it can attach very tightly and it's
Okay,
not water soluble. So you can
interesting.
yeah then you can bind a high number of the density of the molybdenum sulfate to the surface of the cellulose.
Yeah.
It's my idea, I think. Like I
No, I
just want to
think
share
it
with
may
you.
be, it may be like what you're saying, maybe actually it works like the silica or other linkers. So some of the like gluing agents we tried was, uh like polydopamine, which is also like a muscle, found in muscles. It's like a glue, natural glue, but those linkers didn't work. So maybe it's possible that the silica, like you said, SiO2, and if you have other kind of linkers, it may work. So yeah, if that,
But
so
that time
if
the
as
like
long
since
as you have a linker and the MOS to still able to function like the way you want it, then I think it should be a very good strategy to increase the loading.
thank you.
Thank you.
Yeah, thank you for the question. And do you have any more questions? Looks like there's no any questions in the chat. Anyone else want to ask any question? All right, so I have another one regarding the same thing. So in the hexavalent chromium removal, so since you are dealing with groundwater, so have you tested the selectivity towards the hexavalent chromium if there are any other
Mhm.
metals in the groundwater? So
Yeah, um, very good question. I think I didn't get to the part where I like um Pranta Sarkar here mentioned that he's working with arsenic and other like
mhm,
contaminants. So I haven't done experiments where I looked at co-contaminants because I think the most challenging aspect was to create this material. So
mhm,
1 year of my postdoc was just around figuring it out how
mhm,
this works. It looks very simple at the end,
mhm,
but it took some time to get to that. So I think and because our focus was chromium 6, we didn't go beyond it. But for example, we were trying to see how if selenium can be removed, like other metals can be removed. So individually, there may be already some papers that tell you how MOS2 works in a mixed like bag of co-contaminants.
mhm,
But with cotton, we did not look at this. And I think partly because for like California groundwater, when we do the analysis of the groundwater to see what contaminants are present, it is interesting to see that you may have like co-occurrences in some groundwaters. You have co-occurrences of like chromium and uranium together, or maybe there is no co-occurrence of chromium and arsenic. So that's why like we did not plan these experiments, but I think it's worth looking at it. My understanding is that um, currently, based on my research, that only a very small amount of the MOS2 is being used to remove the chromium. So if we have loaded like 5 8%, there is only a very small weight percent that actually interacts with the chromium 6. So a lot of it still remains on the surface that has not interacted with the chromium. So it is possible that if you have more co-contaminants, that we are finally able to use more sites
mhm.
that are like lying around. So there may be competition, or maybe they all get removed. So either one of these can happen. Yeah. Again, very good question. But if I had more time, I would have probably explored, if you have co-contaminants, how it
Mhm.
performs. It's definitely, yeah.
Yeah, so if you explore, I mean, when it comes to research, we cannot stop at one time.
Yeah,
I mean,
yeah,
it's
yeah,
it's
exactly.
expand. I mean, we may not plan at the beginning, but as
Yeah,
we go on, it's going to be like a very extensive thing.
but yeah,
Yeah.
exactly.
So yeah.
I
So.
I agree with you. Yeah.
Mhm. Yeah, anyway, thank you so much, Dr. Mishra, for taking time to share your research with our audience, with our graduate students. So I'm sure I was really interested by your research work. Okay, and it was really interesting. So I hope this helped our graduate student and all the audience we had today. So those who are in the same research, I'm sure they get so much out of your research, the presentation today. So thank you so much and for taking time to be here today.
Thank you. Thank you for hosting me again and for all the good questions, even from the audience. I'm happy to chat if you have any questions via email or like maybe on other platforms. For sure.
Mhm.
Yeah, like all stay in touch. That will be
Yeah,
very.
so then maybe after this presentation, the webinar, I will share the details with the registrants, your
Yeah,
email. So if they have more questions, then they can directly email to you and get their question answered.
yeah. Thank
So
you.
for
Thank you so much.
yeah, thank you for the audience, and this will be the last webinar for the 2025. So we will come again in 2026. So until then, I wish everyone happy Thanksgiving and happy holidays ahead. So see you all in 2026. All right, thank you. Bye.